I think I'm going to try changing this. Oh. So everyone, welcome back. So sorry about whatever was going on there. So this is the last lecture of the semester. So I'll miss giving lectures to all you guys. So after today, there's still 2 more class functions. On next week, Monday, is the second quiz. Again, so it's worth, quiz is only worth 5% of the grade. It's covering stuff from regression, the noise, and the graph analysis. So again, it should be fairly similar in scope and in difficulty and size to the first quiz. So again, it's going to be open book, open notes, open computer, but no communication devices allowed on the computer or otherwise. I heard of some people may have been talking during the first quiz when I wasn't here. This will not be tolerated at all. I will tear up quizzes if I see this during the next quiz. But for others, don't worry about it. You should be fine if you don't talk. If you want to talk to me, that's okay, but not to each other. So it should be things you should not need the computer. Okay, I'm allowing you to have the computer because I don't want you to have to print out all of the notes. You don't need to do any sort of calculations or anything on there. So it should be all stuff that you should, when following class, you should kind of know it, kind of like hopefully on the first quiz. Okay. So the other thing that's coming up is next week, Wednesday, is going to be is going to be the poster session day. So hopefully all of you have now gotten feedback on your posters and sent email to Chris Coleman. Any questions about how that would work, let me know. But he's told me he's started printing all the posters and it seems to be going well. And the posters will be ready and they will be probably I think we'll probably have them in the space we're going to have the poster session at that time or slightly before that. So you won't have to worry about picking them up. But if you want to go visit Chris, he'll probably have them all printed in his office. He's in the back of the SOC main office. And you can probably check it to make sure. Too many people come in and might know him a little bit, but if you want to check, he's usually okay with that. Is there a question about?
Do we need to worry about mounting?
So we'll provide all the mounting stuff. So we'll have easels for everyone and a couple of other things some people like to just put them right in the walls. We have a few ways to do that as well. Make sure you don't damage anything on the walls if you do that. But we'll have ways you can mount them as well. So we'll have everything that we need. Yeah.
Are we going to have like a little desk and a table?
So there should be some tables around. So I'm not 100% sure on where we're going to have the poster session. It's probably going to be in web, in the upper part of web. So either it's going to be in one of the hallway going west off of the Catmull Gallery, which is the big gallery on the first floor. And so then there are some tables along the sides there. Or it might be in one of the classrooms there. It might be in or it might be in Web 1250 or 1230, which is the big classrooms there, and they have tables there as well. I haven't nailed that down. I'm trying to officially book it. The other thing is I posted something on Canvas today. It's marked down that the poster session is going to be from 6 to 8 p.m. That's been on the calendar for a while, so I don't want to change it without consulting with the class and your availability. But that was kind of because we have a weird class time, and that was, I think, the official exam time for this class. But it's a pretty open day, and so I know some of you are undergrad seniors, and that's the senior project day. And so the senior project demos are happening, I guess, that afternoon, like 3 to 5 to 4:30 or something like that. And so there's going to be a bunch of people around. And so I'm going to try and co-locate this so it's right next to that. And so I was thinking we could start at 5 o'clock instead of 6 o'clock. and have the option for people can set stuff up, say around 4:30 or even a little bit earlier, and then some of the traffic from the senior demos would also stop by all the posters. In the past, we've had a few people from outside stop by, but this would get more. So I think doing this would be cool. Yeah.
I think for the senior project demo day, they have the award ceremony or something starting at 5, and that goes to 5:30.
Okay. So I was. That's fine. I was just talking with Jim and Dave about this, and they did mention that this might be an issue. I will. Yeah, they're going to consult on the judging, I guess, from 4:30 to 5, and then I guess the awards are at 5. So if you are a senior and you're doing this, then you wouldn't need to be at the poster during the award ceremony. So doing that would be fine if people are okay with that. If people really want to have it at 6 because they've set their schedules, then I understand that. But so okay, so I think let's. I haven't heard negatively. Oh, other comments.
Could we possibly have it 5:30 instead of 5? Because I might want to be at the award ceremony. Because our group, both of us are seniors, and that means half our team are gone.
Yeah. So I will if you are participating in the award ceremony, you don't need to be there from 5 to 5:30.
Oh, okay.
Right. So what's going to happen during the poster day is there are going to be a few tasks that you as the students have to do. One is I'm going to go around, and I think there's something like around roughly 40 groups with posters, and I have about 120 minutes, so I'm going to have about 3 minutes per poster. So that means I'll be by each poster, and you'll give me like a 2-minute overview of what's going on, and then maybe I have a minute for questions. So you'll have to be there for that. And if you're at the award ceremony, then I'll come to your poster at some other time. So we can work that out. That's fine. The other things you're going to have to do is you're going to be assigned 2 other posters, each of you individually, and you're going to have to go and talk to. I know it's hard. You have to go talk to other people, right? And so you talk to them, and so they will give you an overview of their poster, and then you have to write up a short thing like 250 words. And so you're going to get a sheet with your name on it and a list of all the posters on the front side, and usually you can just write the summary on the back, is what I have intended. So you have to do that for 2 other posters. So half a page of just text.
Per poster or total? 250 per poster?
Like 250 per poster. 250 is just some number. So like half a page each or whatever. I want you to talk with them enough to understand what their project was about. And that means that you have to explain it to other people who come by. So you can also go and talk to other people and see what their posters are as well. This is just so we get an even distribution. Everyone is assigned to some posters and so forth. So I encourage you to go talk and see all the other cool stuff going on in class. Yeah.
So will you kind of give us an outline of when you will be coming around to our poster? Because, I mean, we don't want to...
Yeah.
on
So
somebody else.
usually what I do is the posters usually are kind of around the outside, and I kind of make my way around. So maybe I'll wear like a big hat so you can see where I am, something like that. So you should just be able to tell if I'm coming around that I'm going to be there soon, right? I'll be like 3 minutes per poster, so you can kind of figure it out. But it's kind of unpredictable how things are going to go ahead of time for me. I'm not going to have a fixed schedule. It would take me a minute or 2 to find the next poster if I had a specific order. So I want to give you flexibility to set them up. So I'll post. So I'll figure out where we're going to. Precisely where we're going to set them up, hopefully in the next day or 2, and then put very precise instructions on Canvas and off the web page, so you know about that. And then I'll be around, and the Ts will be around to help kind of figure out how to set everything up at the time as well. And then the last thing you have to do at the poster session is you will get to vote for your favorite poster. And the favorite should be some combination of how interesting you think the work is, as well as how good the poster and the presentation that the group gave of the poster is. So you're going to get to vote for that, and you'll put that on the same sheet. So you'll get a sheet at the beginning. It'll list all the posters, give them each a number, so you can just say your favorite was a certain number. And you'll probably have which poster you're assigned to will be one of them circled. And then the back, you write the short description, and then you also write a vote for your favorite poster. It does not need to be one of the two you're assigned to. So those are the things you have to do, and then you'll just turn in that sheet to the me or the TA, after you're done. So those are what will involve in the poster session. And there's rumor, I can't completely confirm it yet, but if we do this, there should be pizza at the senior project day stuff around 4:30 or so. So if you show up at 4:30, there may also be pizza, so you won't be doing this on an empty stomach, unless you don't like pizza. Okay, so now let's do a vote. So who would? So we'll say either keep it at 6 o'clock or have it start at 5 o'clock with the condition you could be there early, and you can, if you're going to need to be at the Word presentation at 5 to 5:30, that's also okay. So who really wants to keep it at 6? Who wants to move it to 5? Okay, great. We will move it to 5, and I will send out some details on this. So, any other questions about the posters? Yeah.
Are we turning in our poster notes that night, or are we turning them in through Canvas?
It's going to be easier. You just write them on the back while you're there and turn to the TA,
Okay.
and we're basically just going to make sure that you did stuff. Just do it and get it over with, and then you're done with everything. That's what I recommend. If you, for some reason, feel that you can't properly summarize them, and every year a few people do this, you can't properly summarize them on the back of the sheet at that time, then you can send it to us later. That's also fine. But I recommend just putting it on the back of that sheet. Okay. Great. So then the poster session a week from today, and the quiz next week, Monday. All right. So then, let's see. So then the topic of today's lecture is, again, on graphs, but specifically on sparsifying. So on sparsifying graphs. So sparsifying would mean that you have a very large graph and you kind of want to make it sparser. It means you probably want to remove some of the edges but keep the structure of the graph, right? So kind of a history of this is again, if you go back to like this old kind of intuition about graphs, was that remember you had a graph which was these vertices and these edges, and you can say for each say vertex vi in the vertex set, you could have the degree di is going to be equal to the number of edges in E that contain vi. So for the purpose of this lecture, we'll talk about these graphs as being undirected. There are generalizations of this if you want to do it to directed as well. So if you look at this degree, so often if you have if we did this kind of survey in class the other day about the number of friends people had in Facebook, and it seemed that most people had around like the average degree. If you looked at the Facebook graph, average degree was maybe something like, I guess maybe like 200. All right, so maybe that was the average degree of someone on Facebook. They had 200 friends, so you could probably look this up somewhere. So one of the thoughts was that these graphs, people only have so many friends that they ever connect with. So there's these questions of how do graphs grow so we can predict what's going to happen, and we're saying so what happens as the size of V, so this is equals the number of vertices, as this grows, right? So we'll write this as n equals the number of vertices, and so it was thought that in typical graphs that the number of edges in the graph, right? This was the number of edges, was usually going to be about n times some constant, right? So there's some constant, maybe those 200. Average person has 200 friends, so the number of edges should roughly be the number of vertices. So if there are a billion people on Facebook, then maybe there are 200 billion edges in Facebook, right? So that was the thought. And if there were 2 billion people, then there would be 400 billion edges instead. And so people thought this was probably true, that as the graph size grew, the number of edges stayed constant. But so when we started seeing these graphs grow, that people tried to do some studies, and this seemed like it maybe was not the case. There was kind of this large study of these graphs, and it kind of estimated that actually that this was not the case. That instead, number of edges was something like n to the 1 plus gamma, where gamma was usually in the range of 0.1 to say 0.4, I think. Is that what? Or my notes say 0.5. Right, so somewhere in this range. So the most it can be, right, was n squared, right? That would be you're friends with everyone else, right? So this clearly is probably not going to happen in very large graphs, right? But the average degree was increasing, right? So if the average degree was 200, then C might always be 200. Actually, if you look at my notes, and when I first wrote these a few years ago, the number I had was 20. So I thought the average degree of these graphs was even smaller than it looks like, our simple survey of people on Facebook says it is, right? So this seems to be growing as the number of people are growing, but this makes as the number of people on Facebook grows, the number of edges is growing at an even faster rate. So this makes these algorithms harder and harder to deal with. So what we'd like is instead, so by sparsifying, so if we were to sparsify, what you like is another graph H, which is going to be V and say edge prime, where the size of edge prime is again going to be back some constant times n. So not quite like this, but we're going to usually need some like log n term here. Okay, so we're going to say, well, it's going to grow at most log n times some small constant. So it's not going to grow quite as bad, but we still want to capture most of the properties. So we want this graph H to, for most practical purposes, look like the graph G in a lot of the things we want to do, like some various, like doing clustering on it, or finding communities, maybe running PageRank, or finding paths through this graph. So that's kind of the goal of what we're trying to do. We're trying to come up with a sparse representation that even as this grows really quickly, the number of edges grows, true edges grows really quickly, the sparse version does not grow as quickly. Right? So this stays at a manageable size. Okay? And so we're going to talk about two different ways of thinking of sparsifying. One is going to preserve cuts in the graph. So when you cut a graph into two parts, this is really the core of what you're doing for clustering, like spectral clustering. There's some other subversion of this, a bit more complicated. Instead it's preserving the Laplacian. So we talked about the Laplacian was this matrix you can convert. It's not just the adjacency matrix that captures more information, and so there's a kind of a stricter version that's stronger than cuts, and we'll talk about that as well. But these are in the same vein. And then the second version is to to preserve the shortest path. Okay, so we want to preserve the shortest path between two edges. Now, in a social network, this might make sense if you want to understand like betweenness type approaches. Analyze the graph through betweenness. Maybe you reduce it so that the number of edges is smaller, and then that's going to be faster to compute. But where this comes up more interesting is actually when the graph is kind of embedded. And so think of the graph now as, instead of a social network with edges, you think of it as like a road network. So then you want to do routing on this graph. And so you want to kind of reduce it to a simpler graph where the routing is about the same. And so techniques that are kind of, the techniques we'll talk about is like the starting point for how they really quickly do the routing for things like Google Maps. Right? When you do a quick route, you don't want to consider the whole graph. You want to consider only kind of the core part of the graph to do the routing on. And so you want to simplify it first. And so you sparsify down to the core part, find the best graph, the best path there, and then maybe you go and fill some of the edges back in to do some local search. But this will be the basis for kind of getting these algorithms to work really fast. And there's lots of other cool stuff that goes into that, but we'll kind of give the first level of going in that direction. Okay. All right, so let's start with this thing where we are, we're sparsifying for cuts. And so when you're sparsifying for cuts, basically what we want to do is we want to sample edges. So this one is going to be a very probabilistic technique. We're just going to say, I'm going to somehow look at all the edges in the graph and somehow randomly sample some of the edges to keep. Right? So I'm basically going from E to E prime by sampling. So I sample some of these edges, I put them in E prime. The ones I sample are the ones I keep. Okay, and you may want to think of some weights of being on here. So you think of these having a weight on some edge, and you go to a weight E prime. So the simple way is to think that the weight of an edge is always 1. Now you may want to increase the weight over here. So that the idea would be that you start where the sum, say, the sum over all the edges in E of 8 of these initial weights is equal to E prime in here. So you want to preserve the total weight of the graph. So instead of initially them weight 1, you may increase the weight. So now the reason why you want to do that is if you have some graph that looks like this, and so you sampled some of the edges. So maybe I keep these blue edges here. Those aren't really, I guess those are showing up okay. So you keep the blue edges. So it's in this, on a small graph, you're going to end up keeping most of the edges. I may, if I cut through here, the cut on the black edges I cut through 2 edges, so maybe it's better if this blue edge that I kept was worth more than 1. So that maybe its weight was 1.5 or something, so that I'm getting closer instead of having a result of 1. Otherwise, if I reduce the weight of the edges, my estimate of the cost of the cut is always going to be too small. So I need to increase the weight of the edges I keep a little bit. Okay, so if you just look at this, I may not want to sample all of the edges so equally likely. So there may be some edges which are more important than others when I do the sampling. So what sort of edges do you think would be more important that I'd want to keep? Do I want to do this uniform, or how would I define the notion of a more important edge?
Would we look at the degrees of the vertices on either side of the edge?
Yeah, so what's going to matter, I'm going to sample each edge with some probability. So this will be the probability of sampling the edge E, okay? And I want to set this PE to be somehow so it depends, and instead of, so I'll say PE, and I'll say E is equal to IJ. So the probability of sampling this edge should somehow depend on the degrees of the vertices. And I kind of need to do this because if I have an edge that looks like this, that has lots of vertex with lots of edges, I could come up with a cut that kind of goes like this. And so this is probably where I'm going to win. Whereas if I have another vertex that has only two vertices, I could be kind of really wrong if I lost both of these edges. Right? I somehow have more flexibility when there are more edges to play with. It's also because, remember, my goal was to get it so that the number of edges was somehow proportional to the number of vertices. So if there aren't a lot of edges off of this vertex, then I probably don't need to reduce these. I only need to reduce the ones of the really the ones with lots of edges. So I can sample around these so I can make these more careful. I can sample these kind of more or less carefully than I have to around these vertices. So I want to set this so it depends on the number of edges. So I'll do something like I'm going to set some parameter t, and I'm going to divide through by the minimum of the degree of I and the degree of j. So let's say I'm looking at, so if I have, so if I had this case here and this edge connected both of them, I can, whether I kept this edge or not, it's very important for this vertex, but it's not important for this one. But because it's important for one vertex, that means that, well, then I can, this edge needs to be important. So the smaller, so if there's a very high degree on both of the vertices, then there's a very small probability of keeping it. But if any one of the vertices has a small degree, then that edge becomes important. Yep.
If that's the only edge that's connecting two communities, does that edge become more important?
So it kind of does in some sense. In the cut sense, whether the cut is 0 or the cut is or if the cut is 1, doesn't really make that big a difference. Those are both small numbers. It's still a good cut, right? But it's kind of so it seems like it's important though. It seems like that part of the graph you can be more careful about. The problem could be that you could have a bunch of these disconnected vertices that each have two edges, and then I can construct a cut that goes through here. And if all of them I lost the edge, I could be in trouble. Right? If I go a cut around this vertex, I either need to cut all of the edges or some fraction of them that connects to something else. So here I can't come up with these bad cases. If I have a cut that goes right next to a bunch of these low degree vertices, then I want to make sure I keep all of them. The other way to think about it is that I can charge each vertex to each edge to the smaller degree of the vertex. And I said I want to keep, so this parameter t is going to be, basically I want to keep t edges per vertex, roughly. So this t will be this constant times the constant times log n. And so I want to keep t edges per vertex, and so if I have a low degree vertex, I should be able to keep all of its edges. And so in the case where my graph is already very sparse, then this should mean I don't need to cut any of the edges. Only if I get these really high degree vertices am I allowed to cut edges. And these high degree vertices connecting to other high degree vertices. This is where there's a lot of kind of repetition going on in some sense. right? So this would be kind of like I have a very dense community, and so cutting that community in any way should be hard. So I can think of saying, well, if I weighted all the edges in the community, then any way I cut it is still going to be very costly. But if I have these disjoint communities, I want to kind of keep those sparse edges in place. So I know all the different ways of cutting across communities is preserved well. Okay, so probably to look something like this. If you look at this expression, and this is a probability, what could go wrong here? Why can't I just use this expression for some value t? So t is going to be something like some constant times log n, and I'm going to have the property that the number of edges is going to be less than or equal to t times the number of vertices. So that's what this t parameter is going to mean. What could go wrong if I set the probability equal to this?
It can be greater than 1.
Yeah, it can be greater than 1. That's right. So probability has to be between 0 and 1, right? So I have to fix this. So what I say is that it's the minimum of 1 and this value. Okay, so if this probability is greater than 1, which means that it's attached, one of the vertices it's attached to has degree less than or equal to t, or less than t, then I always keep it. If I keep it with probability 1, that means I always keep it. So I don't want to say I keep it with probability 2. That just doesn't make sense. So I have to kind of fix it by saying the minimum of 1 in this value. Okay? And so then, if once I set it this way, you should see that you can see that the number of edges is going to be, I guess, in expectation, depending on how I do the sampling or exactly, is going to be less than t times the number of vertices. Because for every edge, I can say, let's assign that edge to the vertex which has a smaller degree it's connected to. Okay, so every edge is now attached to one vertex, and for each vertex, I'm now going to select t edges from it. Right, and in expectation, and so each of those edges, so then I select t edges from it, and this is the number of edges I get. Right, and so the probability of selecting an edge is only going to be less than that, because I have multiple ways of choosing it. No, I could have more edges per vertices, but I can always assign to the smaller one, right? So you should be able to kind of see that the number of edges is not going to be too big. I can control it by this parameter t. Okay. Does that make sense? Okay, so it turns out if you just randomly sample edges according to this probability, and you should be able to compute this. Typically with these graphs, you want to do this quickly. And so one information you have is for each vertex, you should be able to calculate its degree pretty quickly. That should be stored on the system somehow. So you have these quantities, and you can assign these probabilities to these edges. And then you go and you say, you flip a random coin, or you generate a random number between 0 and 1. If it's less than this value, then you keep the edge, right? So you can do that then for every edge, and this gives you this E prime. And so the property this is going to give you is going to be that, so for any cut, so if I, so this is for any cut C, and I'm going to break the graph into two components, S and T. Right, so if this was the graph and this was my cut, then this would be S and this would be T. Right, and so then the edges, if you remember how we talked about dividing these graphs, the edges across the cut are going to be this edge and this edge here, the ones that go across the boundary. Right, so then if I sum over all of the edges in this cut, and I look at the true weights, and then I subtract the edges in the cut, and I look at their new weights here. I want this to be less than some parameter epsilon, which is going to be in 0, so some value between 0 and 1. It's going to be 0 and 1. Epsilon times, let's write that this sum should be equal to W. So this should be epsilon times the total weights, which is going to be in 0 and the total weight, right? So I can set some parameter, fraction of the total weight that I want to preserve here. So in order to do this, I want, so implicitly if an edge is not kept, its weight is going to be 0. And so I want to set the new weights so that I get this property, right? So how do I set these new weights? So if it's, yeah, so I set the new weight of an edge. So I'll set, so I set the weight of the edge is equal 1 over the probability of E. So if I kept it with probability 1, then it's kept the same weight, right? This is for the unweighted case where all edges have weight 1. So if I kept it with probability 1, then the new weight is 1 over 1. If I kept it with probability 1/2, the new weight is 2. Right, so that's how I get these new weights, and I'm going to get this guarantee if I set t large enough. Turns out you need to set t, this is for t equals to 1 over epsilon squared times log n. And I think there's some constant in front here that I don't have written down. So 1 over epsilon squared times the log of the number of these vertices. Okay, so this is a kind of a pretty kind of, it's a very simple technique, and it seems like a very cool result. So what do you think of these bounds, right? What does this make sense? I set t equals 1 over epsilon squared times log n, and I get on any cut epsilon times the total weight is my error. Does this seem useful? So let's see. So let's say that I wanted to keep the total weight, or the average number of edges to be, so if I had a billion nodes in the graph, and let's say this is a log base 2, so log base 2 of a billion is going to be roughly 30, right? So we'll say log 2 of 1 billion is roughly 30. And so then I want, say, the average, so then I want to set this epsilon to be 0.1, right? So I want 10% error on a cut. That seems like a very large amount of error. But then that makes 1 over epsilon squared equals to 100. So that means that t would need to be equal to 3,000. So I can guarantee that if to get 10% error, I'm going to get no more than 3,000 edges per per vertex. So this kind of seems like a lot. So if you had a much richer graph where it's starting to get fairly dense, and this may not occur in most normal social networks, where you're getting, say you had a billion vertices and you had like a million edges per vertex on average, then this seems like this might start to become useful. But otherwise, you're going to need a large number of samples to get these guarantees. In practice, this probably works a little bit better than these guarantees. But the sparsifying in this way is actually pretty hard to do. So this kind of idea of sparsifying by sampling edges has been around for a while, and people have tried to improve it. But it seems hard to get beyond some numbers like this. So the other way I'll talk about where you're doing the shortest path sparsifying is going to be more on the practical side of things. But before I move on to that, let me mention this version that has to do with the Laplacian of the graph. And this version is kind of an extension of this technique, and that you can think instead of just the Laplacian of a graph, you can think of the Laplacian matrix comes up in a lot of like numerical computing, where maybe you actually have a dense matrix, which you think of as a Laplacian, and then you're sparsifying you're making most of the entries 0. If you can set 90% of the entries to 0, that might already be like a big win, and if you're doing some linear algebra on these very large matrices. So the idea is to preserve the Laplacian. And so when we talked about spectral clustering, there were 2 types of the Laplacian here. We're going to talk about the unnormalized way. So we have, say, a graph LG is going to be the the Laplacian is going to be the degree matrix minus the adjacency matrix. So the adjacency matrix is what we're thinking of kind of as just storing which edge is connected to which one, and the degree is just going to be the diagonal matrix, which is the degree on this diagonal. So this one is going to be D1, D2, and so on, and these are all zeros, and these are 1, 0. It's probably going to look something like this. And the adjacency one should be symmetric, so that this is also going to be symmetric. So the goal then is to get another Laplacian so that the LG minus LH, the 2 norm is going to be less than or equal to epsilon times the total weight here. And so instead of this, so if we think of the total weights, let's just normalize this so this is equal to 1. And so that will kind of simplify some stuff. This 2 norm means that 1 minus epsilon x transpose LG. I'll write this up and then kind of give intuitive explanation of what this means. Okay, so what this is saying is that I want the so now x should be a unit vector. Okay, so an example of an example of a unit vector would be one where would be a cut vector where the values are alpha, 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 0, 0, alpha, where these alphas are going to be all the same value, or you're going to have a 0. And so the alphas are on one side of the cut and the zeros are on the other side. So this unit vector, if it's a cut vector, it basically is saying that I'm dividing the vertices up into 2 parts, and it's either one side or the other side. So I'm essentially assigning each vertex to be on one side or the other. It's kind of it's binary. But in general, this x could be a unit vector, so these could be any values here. So that was where I took some graph, if you remember this, what the spectral clustering was doing, and it was drawing all of these vertices down onto a single one-dimensional kind of some one-dimensional line. So it was centered around 0 here, and then basically the cut, whereas this was S and this was, say, T. So this was the cut. You take the left of 0 was 1, greater than 0 was the other. So I guess you could also make these minus alpha or plus alpha. So you could think of that being that way as well. But or it could be 0 or alpha. But anyway, a cut vector is one way of doing this, so that you project them down into one-dimensional space, except it signs them all. The cut vector, this one, would say that all of these map to here, and all of these map to a single location over here. Okay, so it's saying it's either at 0 or alpha. But the Laplacian says for any vector, I want to maximize this. And so the best way of projecting them into one direction is the x, which maximizes this. So this is for all x, which is a unit vector, you want this property to hold, and in particular for the best possible x. And that's the one that gives you this cut. So this is kind of a stronger property that people that people are after. It's staying more than the cut. So if you can preserve this property, then you can get these. You're preserving a lot of information about the matrix, not just how to divide it into two parts. And so this is useful for kind of things like when we're talking about the matrix sketching for approximate PCA and stuff like that. There's some similar approaches that want to minimize the Laplacian for various reasons. And so one way people have found that you can actually get this property is to change the sampling probability of an edge slightly. So it's again the minimum of 1, and I'm going to write this down. So it's a minimum of 1 and essentially some constant times the so it's known. So this is going to be what's called the effective resistance. And so the idea is you want to treat this original graph here as like a circuit. Like if you're like one of these electrical engineering people, I think there are a few electrical engineering majors or grad students in here. So think of this as a circuit, whereas if you put current through this graph here, you want to say how important is this edge. So if you have multiple ways to get from here to here because there are two paths you can take, then the effective resistance of any one of these edges is lower than if you have this edge here, right? So if each of so you can think of having so if you have a so if you have a graph A, B, and C, the effective resistance between A and B, and this says weight 1, 1, and 1, is then going to be equal to, it turns out to be is going to be 1 over 1, which is this edge, plus 1 over 2, which is going through C and then back down again. So you're going to get a number that's going to be 2/3. So this has less resistance from A to B because you have this alternate path here. The more alternate paths you have to get from A to B, the less important this individual edge is. So you want to sample more if it's the only way to get from A to B is to go through this edge. Then you want to sample with probability 1. If you have multiple ways to go from A to B, then you should have a lower probability of keeping it. Right? So if I want to cut, so A and B are on different sides of the cut, then it matters a lot, this edge, if it's the only edge that I want to keep. And so if you calculate this effective resistance, which is not simple to calculate, but if you can calculate and you sample with this probability, then you're going to get this stronger property. And so people have been trying to figure out ways to do this efficiently, but you still need these high constants in front of the number of edges you have to sample. But there's been a lot of work in this area, and so they're trying to get the constants down, and this is something that I think we'll see a lot of resolution in this area in the next probably 5 years or so. Okay, so that's what I wanted to say about these sampling, preserving these cuts, and these Laplacian approaches. Again, you either set the probability based on the degrees or based on this effective resistance of the edges, but that's harder to calculate. And you can get stronger guarantees sampling that way than you do with just the degrees. Okay, so let's move on to this other way. And so this is to preserve the shortest path. And so these sorts of sparsification is what's often called a spanner of the graph. Okay, and so this is the one where we think of like modeling the graph like a road network, and we want to keep the important edges. And there are ways of generalizing this to say that kind of a highway edge is more important than like an edge on a back street, or somehow the weight is higher. There's a way of translating that, but we'll just talk about if they all have equal weight edges associated with them. So now, in order to preserve the shortest path, we need to kind of define what this is. So we have a graph again, and so we want to define a distance on the graph between vertex 1 and vertex 2. And so, and now it's useful to think that this graph is actually embedded, right? So we have, so say it's in R2, and then we have these vertices. And so sometimes we can even think of that, so say we're like building small houses in the middle of the Salt Lake, and we have to build roads between the houses, right? So we could build a road anywhere, but we only want to build just enough roads where people can drive between the houses, right? So we could draw any possible road here, but we only want to draw a small number of roads so that if I look at any vertex, I can get to any other vertex without having to go too much further, right? This vertex to this one, I have to go through the central place, but otherwise, if I went from here to here, going through this other node instead of going straight across is not going to be that different. Now, the other option is I can start, so one way is I can start with the graph that's complete. I can say every edge is in there, and I can assign a weight to the edge. Or I can assume that the true distance here, so this is either based on the graph. So one way of defining this is if I only consider edges in the graph, then this would be equal to the min over all, say U, which is in the neighboring set of V1. It's going to be the distance from U to V1 plus the graph distance from U to V2, right? So I can define this recursively. So if I'm at V1 here and I want to go to, say, V2 up here, I can either look at, I take the minimum over all the neighbor set. The neighbor is either U1 or U2. And I look at the distance to U1 plus the graph distance here, or the distance to U2 plus the graph distance, which happens to go through U1, right? So if I'm restricting to this original blue graph, maybe I want to sparsify and get rid of this edge and this edge and this edge, and maybe doing so is not so bad. So I could sparsify, say, get rid of these edges further, or I could say I start with the complete graph. So what I want to do is go to another graph, H equals the same vertex set and a smaller set of these edges, so that I get a new graph distance dH, which is defined basically the same way as dg, right? So this defines the shortest path on the graph. Okay, so does this definition in the problem make sense? Yeah, I want to preserve all shortest paths. Yeah, so I want to say, so I want to, specifically I want to say for all, say, A and B in the vertex set, that I want this property, that I want 1 is less than 1 plus t. Okay, so if I look at this distance is always going to be larger. If I remove edges, I'm always going to have a longer distance because there are some edges I can no longer take anymore. And but I don't want it to be too much larger, and I want to make this relative. I want to make it so it's proportional. So let's say t is a value, say like 2. If t is 2, then the length is no more than 3 times as long as the original length. Right? So if t is equal to 1, then it's no more than twice as long. And so if all these edges are of length 1, then I can remove all the red edges and I'm still going to be okay. Right? If I went from u2 down to u1, the distance used to be 1, now it's 2. If I went from u2 to this vertex over here, let's call this b, the distance used to be 1, 2, now it's going to be 1, 2, 3, 4. It's twice as long. That's still okay. Now I could set t to be less than 1 also, which means that all the short stuff I need to kind of keep for locally, and sometimes that's even going to be I don't think that's possible if I have if the edges all have length 1. If you take out one edge, you're probably going to at least double the length. But there's some cases where the weights are not all 1, and then it makes sense sometimes to set t less than 1. But in general, relative error, maybe the cost is no more than twice as much. That's not so bad, at least for an initial guess of what's going on. Okay. And so if you think of like if you're dealing with highways and stuff, then or what you may do if you're like routing for like Google Maps is that either you route locally on some small complete graph which you have in memory someplace, or if it's long distance, then you have a simplified version where you start with these approximation, and then maybe you can refine locally with the rest of the graph. Okay, so I want to somehow simplify it this way. You kind of see this is a different notion than the first version. Okay, so how would, well, okay, so let me, before I say how to do it, and how to do it's actually going to be even simpler than before, at least a few of the ways. There are a few things that I want to do, other than, I mean, first of all, I want to make this value t small, right? So that's the goal. I want to, so if I keep all the edges, t is 0, which is great, but that's probably too restrictive. But I want to make the number of vertices. I want to make the number of edges in E prime, I want this to be small. So the number of edges I keep, I want that to be small. And maybe this is, again, something like log n. Sometimes you can make this a constant that maybe only depends on t. So I want the total length of all edges small. So I don't just want, so if the edges have different lengths, right, say they had to do with the actual distance, I don't want to keep a lot of long edges. I'm okay keeping a bunch of short edges, but I don't want to keep a lot of long edges in there. So think of if you're constructing a highway, then you don't want to have lots of duplicate highways, right? And then the fourth thing is I probably want the max degree also to be small, right? And if you're thinking of a road network, you may want the max degree to be 4, right? You don't want to have intersections that are like 10-way intersections, which probably be crazy. There's some places like under freeways now, and some places they want to have these high degree intersections. I don't know, if you go up to like to Park City, there's one that has I think effectively it has like an 8 degree, and there's one by, I think the exit in Lehigh, there's this new intersection where they have one stoplight for a freeway exit. It's pretty cool. But it's actually a pretty high degree thing. It's just the traffic can flow multiple ways whenever the lights are green. But anyway, so you want the degree of these typically to be small. And this makes routing easier in various ways. Okay. So these are some other constraints other than just t small and the number of edges small that you want to in your design. Okay, so how would you construct such a graph? What is kind of we're not going to do something as kind of blunt as just sampling the edges. We can do something a bit more, yeah.
First search, find the shortest path and then take all the highest, all the ones that aren't the shortest path. So you make it basically.
Yeah. So which shortest path do you look for first? Like between which two vertices?
Wouldn't you need to look at every vertex to every other vertex?
So look at all shortest paths, and then, yeah. If you wanted to do that, then if like in the complete graph, you're going to have all of the individual edges between every pair of vertices. But if you do something similar, you find the shortest path between any pair of vertices, and keep that first before you put that edge into the graph. And what this is just the shortest edge, right? So if the edges all have distances on them, so instead of thinking of them now as a weight 1, think of this as being the Euclidean distance between the two vertices. So find the closest two vertices and put those into E prime. Okay, so basically sort all edges by length, and so it turns out you won't actually need to formally sort them, but you can kind of start by kind of getting all the closest ones, sort them by length, and so also start. How about I just make a new page here? So we're going to do a greedy spanner. So, and this is from G to H, where this is V E and this is V E prime. So start with E prime empty, and then so sort all E in E by this length of E. So the smallest first, okay, and then if say D of H of the length of this edge, D of G is less than 1 plus T, then, or is, let's just say is greater than 1 plus T, then put E in E prime, okay? So we're going to sort all the edges from the shortest to the longest, and then and remember H starts as empty, right? So this is going to be infinity if these two parts are not connected, right? So if this is greater than 1 plus T, which means that it violated the property that we wanted, then add that edge, okay? And then move on to the, so then we're going to process these inside of a for loop for E and this is in the sorted order. So if it violates this property, then you add it. And then you move on to the next smallest edge and you add this. And you keep adding edges until you find that this is not a problem anymore. And if this is otherwise don't put E in E prime, right? I don't need to add this edge if this property is already true, right? If the distance between if the distance along the edge was already small enough, then using the edges I already had, then I don't need to add this other edge. Okay, so this is guaranteed to satisfy this property, and it turns out this works. This works okay. So this works reasonably well. So it's not going to give the optimal approach according to all those properties that we wanted, but this is a pretty good kind of first way of doing this. It's hard to make certain guarantees about the size of this, and if all the edges have length 1, then you're kind of up to some kind of, well, I guess, right, again, in this case, we're thinking of they have some Euclidean embedding, and their length is the Euclidean distance. It's hard to make guarantees on the size of this approach, but this works fairly well. Okay. There's another kind of cool approach. So this way you have to kind of iterate things in order. You kind of want to decentralize this a little bit. And there's this other way where you take a vertex V. So this is the greedy way. There's another way called the cone approach. So you take a vertex V, and then you divide up the space into these 6 regions. You can get different properties if you do more than 6, but you need at least 6, where each of these angles is going to be 60 degrees. Okay. Then if you look at the underlying graph structure here, or you're going to think of having a lot of these vertices possibly out here. So which edges do you want to add on for this vertex? Well, you look in every cone, and you're going to find the closest point in every cone. Some cones might be empty if it's on the boundary, but so I'm going to add at most 6 vertices to each. It's 6 edges to each vertex. So I find the closest point for each vertex, and I add that into the graph. So I don't add any of these long edges, because there's something closer here. And it turns out you can get these nice guarantees that the size of this, I mean, clearly the size of this is going to be at most 6 edges per vertex. You get some bound here for t. I think this gets the property that t is going to be less than or equal to 1 over 1 minus sine of theta over 2. So this is if you set the angle, this angle here, instead of 60 degrees, if you set this to theta, then you're going to get this bound for t. It's kind of a pretty cool property. And the smaller you set the angle, then you're going to get a smaller and smaller bound for t. Of course, you're going to get more edges. Yeah.
But this method assumes the graph has a geometric.
Yeah, right. So this is the setting where we're thinking geometrically. A lot of this makes sense usually in a geometric setting.
But like for social network.
Yeah, so this is not really useful for social network. The greedy approach works, but it's really hard to make any real guarantees for if you don't have an embedding in this approach. You may, like if all the edges are of length 1, then basically the best thing you can do is some random greedy approach, and you're just going to, I don't know, it's kind of, the greedy algorithm is probably about what you can do. If you have, they're kind of, if you don't have an embedding, I think you can make this problem pretty hard. You may need to keep almost all the edges. There are these things called, these types of graphs called expander graphs, where, and real social networks are kind of like this, but the idea of expander graph is the degree of every vertex is relatively small, like something like log n, but you can get to every other vertex in a small number of steps, so that the distance is always a constant. So maybe if you've heard of like this, if you've heard of like this small world phenomena, so has anyone heard of this? Right, so this is the idea where everyone knows someone else who knows someone else, and if after a small number of steps, you know someone who knows every other person in the world, right? And they've done these studies like where they gave, this was pre-internet, but they gave these random people in the U.S. I think the name of someone and like the city that they lived in.
Like a lawyer or an accountant. They
What?
gave them the name of a lawyer or
okay.
an accountant, and then they sent them 6 letters, and then they asked them to send them, to make 6 copies and send them to other people till it got one of them. Like eventually, some of them got.
Well, so I think the goal was to send a letter to someone you knew, but you had a target destination, right? So if you said, well, I know this person lives in some small town in Ohio, then I'm going to send it to a friend of mine who lives somewhere in Ohio. Then they send it to someplace near that small town, and they found that all the letters got there, and like people participated really well, and it got there in like 7 steps always. Right? And there's this notion of small. You can always get someone a small number of steps, right? And this shows up in social networks a lot. You can often get to almost anyone else in a small number of steps. It seems 7 seems small, but it's actually you can get really far with 7. There are some weird, really isolated people who intentionally isolate themselves, so maybe that's not always true. But like there's also these things like on like if you hear of like the Oracle of Bacon, or like the 7 degrees of Kevin Bacon, where any actor who is listed on IMDb, there's a connection of 7 movies that they've been in with another actor, and eventually you get to Kevin Bacon, right? I had a friend who used to he might still maintain a website where you can type in an actor and it'll use IMDb to look up the shortest path. You can do this people do this with citations in computer science with like with Erdos, right? So you have so everyone has their Erdos number. How many papers you have to write with someone else to get to Erdos? I think mine's like 3. So my advisor wrote a paper with someone who wrote a book with Erdos or something like that. So, but anyway, so these come up in graphs all the time, and so this makes this really challenging in these social network settings. Road networks are not like this, right? You know, unless you can get on I-80 and then go all the way across. I guess that counts as one edge, right? But in the road network, they'd actually think of the I-80 as many, many edges strung together, right? So, so you don't get these properties in road networks, and that's kind of what allows you to do this. Okay, I quickly want to mention one other way of doing this, and so this is a really powerful way. This is called a well separated pair decomposition. Okay, so, or a TWSPD. That's a little bit easier. And so the idea is we're going to kind of do this in a hierarchical way. And so if you remember like these KD trees or quad trees we talked about for doing nearest neighbor searching, you want to do that with your data in this way as well, and then use that structure essentially to build this spanner. So this well-separated pair decomposition is a really cool thing that has 4 properties. So it starts with it's of a so you do this of a, you just think of a point set. So you start with the complete graph of a point set, and let's say it's an RD, or you can think of it as it's in 2 dimensions, right? And so so you're going to break a well-separated pair decomposition is going to be a set of pairs. So this is a set of these pairs, and so it's going to have that A and B are both going to be subsets of P. P is your vertex set. It's going to be that each edge or each pair of vertices in the edge set. So this is going to be it could be the complete graph. It could be a restricted some edge set E is in exactly one pair A, B, okay? And then the third property is you're going to have the distance between A and B, and this is going to hold for so that means this vertex, these vertices are in exactly one pair. And if you look at that pair, so the min of A in A and B in B, so A and B is going to be greater. So the distance between, so you're thinking of some set A and B, and the shortest distance here is going to be greater than T times the max of the distance from A1, A2, where these A1, A2 are in A, and D of B1 and B2, where this is an A. Okay, so that means if I look at this distance here going across, or here, that this is at least T times as long as this minimum distance here, right? So I can take this blue part and I can lay it down, say, T times. So this would be for T equals 3, right? So if I take the longest distance here, so basically I'm dividing the data up into these pairs so that all these in A are close together, B is close together, and these sets are far apart from each other. Okay, so I somehow want to decompose all of the points into all of these pairs. And then basically the spanner, so I'm going to get a T spanner by, I'm going to get the edge set E is going to be one edge AB from each pair AB. So I'm going to decompose it into pairs like this that are all tightly coupled on each side but far apart, and take any one edge from each of these. And this will give me this T-spanner. And it's going to have a lot of nice of these properties here. And it turns out you can create a T-spanner where the size of it, so meaning the total number of edges that you keep, you're going to have the size is going to be equal to basically roughly T times the size of the point set. So you can make this or T to the power D. So as the dimension grows, it's going to be, you're going to need more and more points. But if the dimension is small, then you're going to get, or this is, yeah. So this is, as the dimension is, actually this is going to give a 1 over T spanner, or this T is different than the T in the spanner, but it's somehow relates. I think this T is so this you're going to get a 1 plus epsilon spanner where T is equal to 1 over epsilon is the property that you get. This is going to get this property by selecting one vertex from each edge. Okay, so this seems like a really crazy kind of thing that you want to get. This same concept comes up in many different things. If you've heard of like the multipole method in numerical computation or n-body problems, this is basically the same thing that they do. And how you do it is you build this quad tree. So all your data points need to lie in some big. You put a big square around all the points, and then you keep dividing this square up into smaller squares of equal size. And so once you do this, you can think of building a tree on top of this. So this is a 4-way tree. And then I divide each of these further down into 4 parts, and so forth, and I get a degree 4 hierarchical tree. And at any time when I divide, I check this node in the tree. I try and see, does that satisfy a T-spanner with another node here? So I look at, say, this node in the tree, which corresponds to here, and maybe it's a T-spanner with this whole other node here. If there are no points over here, maybe this actually works. And so then if this is, then this would be a pair. And so I kind of build this tree as I'm going down. I try and match up these pairs, and once I do that, I can stop. I don't have to, if I match up one of these nodes with every other pair, I can stop recursively going down except for matching stuff up with itself. And eventually I can stop when the constant size in the pair, in the pairing. But you can kind of build this up recursively, and this creates these nice T-spanner things as well. And so this is a nice way of decomposing this.
So I did have a question. So, I mean, in building a quad tree, obviously, you can use this data structure. But have people found success in using like hierarchical clustering, defining different metrics?
Yeah, so hierarchical clustering, one, is pretty slow to do. I know some of you tried to do this for your project on these big data sets. It's really slow. And so it would you probably could get it to work a little bit better, but it'd be hard to prove much more about it that it really always works. It might work in practice really well. So in terms of cities, they definitely do that. They build a spanner for each city, and then they build these legs, these highways, these connectors between the cities. And then they do this down recursively to some degree. There's some aspect of that in the road networks. In general, this technique is kind of fairly powerful. And you can get this to work pretty well. But across the boundary, it may not work so well across these boundaries here. But what's going to happen is you're going to have to go far enough down before you create this pair. So it'll end up working well. It's going to arbitrarily split them at some point, and maybe you don't want to do that. So we've run out of time for the lecture and for the semester. See you on Monday for the quiz, and then we'll see you on next Wednesday for the poster session. I'll post some details about that on the webpage in Canvas. So. Thank you.